Okay, we'll go ahead and get started. So we're now into module 3, and the big topic of this is physical organic chemistry, and that's going to drill a little bit deeper into the concept of acidity. We'll start learning how reactions happen through mechanisms, so how do electrons move? And that really relates to these different theories of acidity. We'll kind of use some of them interchangeably and see the limitations of probably what you've learned from Gen Chem. And throughout this module, I would definitely encourage you to start using your model kits to build models, because we want to start thinking about these things in 3D. So we'll get into conformational analysis. So these sigma bonds rotate. How does that rotation affect the reactivity of the molecule? So there's sort of the normal resting state or ground state of a molecule, and then there's the reactive state, and they are not necessarily the same thing. So we'll start talking about energies. So we'll get into bond energies. What are easy bonds to break? Why do reactions happen? What drives them? So a little bit of kinetics and thermodynamics. And then this module will finish on this concept of stereochemistry. So when I was drawing those wedges and dashes for bonds, that's going to have another meaning as we examine the substituents bonded to carbon. So at this point, we are rowing further and further away from shore into deeper waters. So you definitely want to make sure that you can look at a molecule and dissect it and figure out the molecular formula, what functional groups are there, kind of make that association between the functional groups IR, mass spec, and NMR, because now we're going to add some more layers to that. And through that, the goal is to make the understanding of the reactions that we learn very rational, in the sense that if you're giving a starting material, some reagents, what is the product? How do those reagents act upon the different functional groups? So it's not random. It's based on all this foundational material. So we'll get started, and as I promised, I will do some Excel accounting and move your scores from zip grade, put them into Canvas, and then upload your interim grades into SOAR. I don't know when they release them to you, but I think my deadline is Friday at 5, so I don't know when you get it, but you'll have those available to you for your advising. So what I thought we would start with is kind of a brief review of acids and bases from general chemistry. So the stuff that you learned in Gen Chem is setting the stage for organic. Acidity in organic, as I said, it dives a lot deeper, because now you've learned all these functional groups. And so from the big picture, we can think of strong acids. That's the stuff that you learned in Gen Chem. Organic is really all about weak acids, which are the different functional groups that you've learned. So let's put these categories into perspective, and through that, we'll have to talk about water so that we can dial in about what is it mean to be strong versus weak. So from your recollection of Gen Chem, is sulfuric acid a strong or weak acid? So it's a strong acid. And what about acetic acid? Have you heard that term before, acetic acid? So that's acetic acid. That's the common name. It has a different formal name. We'll sort of learn some of that in maybe this module or the next one. But it has 2 carbons. It's a carboxylic acid. So 2 carbons is ethane. This is called ethanoic acid. And so is that a strong or a weak acid? So this one's weak. It's actually vinegar. So it's in Italian salad dressing. So the oil in vinegar is, the tanginess is acetic acid. So you can eat it. You can clean rusty pipes with it as well. I mean, it's a good solvent for things like that. So there's sort of 2 examples of strong versus weak. And so which one is stronger? Obviously, the sulfuric acid is stronger. So what I want to draw your attention to is if we look at these structures, and I'll switch to the highlighter here. They both have that OH. And so the H of the OH is what is acting as the acid. If that is the same thing in both molecules, why is there a difference in strength? Why is one strong? Why is one weak? And so to consider that, we'll look at the rest of the molecule. So I'll do that one in blue, and then I'll do this one in red. So how does the rest of the molecule that's highlighted in blue for sulfuric acid and red for acetic acid, how does that increase or decrease the acidity of the H of the OH group? So we're going to look at the factors that affect functional group acidity. And so this gets back to a couple fundamental concepts. One is electronegativity, the second is resonance, and then the third is induction. So for acetic acid, how many unique sets of hydrogen does it have? So it has 2 unique sets, and they would be in a ratio of 3 to 1. And let me just highlight this. So there's the 3, and then there's the 1. So when we say acetic acid, we're thinking of that H as the acidic proton. But we have 2 sets. When you did this exercise, every set of hydrogens that you figured out, it is acidic. Now, as I said, with organic chemistry, we're dealing with weak acids. So the range of acidity is very great in that weak acid spectrum. So when you look at this, you say, yeah, that's the acidic one. But these ones in blue are also acidic. And as we start to learn about reagents and things, so if both of those sets are acidic, we would need different types of bases to deprotonate each one. So how do we match acid and base strength? So something that readily deprotonates this H will not deprotonate these H's. So with the different functional groups, they're different acidities, so we have to learn different bases to match those functional groups. So acetic acid can react with sodium hydroxide. And we can use the solvent water to dissolve everything. And then we'll get an acid-base reaction. So one thing we'll review is this acid-base, conjugate acid, conjugate base. And so we need to be able to do that to compare which side of the reaction is going to be favored. And so that will get us into this concept of equilibrium. And even though the word equilibrium has equal in it, that does not mean 50% of starting material, 50% of product. It means at some time there's going to be this state set up where things, either go all the way towards the products or they don't do anything at all, and then all the scenarios in between. So it doesn't mean starting material and product are equal concentrations. So we'll have to wrap our head around that. How can we affect the equilibrium? So remember, like Le Chatelier's principle, that concept. So let me draw, I'll draw just the products of this. I'm not going to show you how it happens. We'll do that in a little bit. But we have an acid, and therefore sodium hydroxide has to be a base. And what I really want you to pay attention to is, the sort of the verb action of those reagents. In one definition of acid-base reactions, a base will abstract a hydrogen, and an acid will donate a hydrogen. So that's one theory or definition. So if we say of the two sets, that one is the most acidic, the base is going to abstract that. And when it does, we end up with that species, and then we balance everything off, we get water. So I want you to pay attention as well. So see sodium hydroxide. So sodium is a cation, hydroxide is an anion. The sodium's what we say just a spectator. So notice it's Na+, it still ends up as Na+. Nothing changes with it. But that negative charge on hydroxide now ends up on this oxygen from the acid. So we have plus minus, and then we end up with plus minus. So as we start learning about mechanisms and accounting for electron movement, we have to make sure that we're not generating an excess of charge, because it's not allowed. So sodium hydroxide will deprotonate that just fine. However, it will not deprotonate those. It's not strong enough. but you can deprotonate them. So what we have to learn is what sort of base do we need to deprotonate those type of hydrogens. And another thing I want to point out, related to that first slide, when you look at, acetic acid, we can recognize that is an sp3 hybridized carbon, so it's sp3H. So as you look at molecules, always try to, review those concepts in your mind, because as you do that, you're going to be able to rank acidity. So really, what are we dealing with all the functional groups we've learned? So OH, NH, and CH. With OH, there's alcohols or carboxylic acids. With NH, there's amines, there's amides. Then with CH, how many different functional groups with CH did you learn? Quite a bit. And so they all have different acidities. So as I said, the functional groups that we've learned so far are all weak acids. And so to deprotonate them, we need strong bases. And there's a lot of different bases that we'll learn, and so we sort of match them appropriately. But what I've shown on this slide are two molecules, gifritoxin, that natural product, and apixaban, which is a prescription drug. And what you can do for practice outside of class is figure out the molecular formula, what functional groups are there, how many sp3 hybridized carbons, sp2, sp, what are the attached hydrogens to each, so methyl, methylene, methine, or quaternary. Are things sort of saturated, or are they aromatic? So in comparing those, that CH2 group versus this CH, the difference is the carbon hybridization. And for all of these hydrogens, you're going to have a huge number of unique hydrogen sets. So within each set, you can assign a functional group, and then as we'll learn, you can assign an acidity to it. When looking at either of these molecules, basically what you're going to do is sort of rank those functional groups and say, if I treat this with an appropriate base, which hydrogen gets deprotonated first? And so that's the rational part of how to make molecules. What reaction happens first? So it's not kind of willy-nilly in the sense that, say you wanted a reaction to happen here at one of these hydrogens. That would be very difficult to do because there's a lot of other CH2 groups in the molecule. So we have to move sort of beyond wishful thinking and categorize these things according to the functional groups to know where exactly a reaction is going to occur. So to set the stage for the weak acids, let's just review some concepts of acidity so that we kind of know the scale that we're going to be dealing with to do that. And we're going to start with water. So we all know about water. We can calculate the molecular weight So oxygen's 16, hydrogen's 1, so we get 18 grams per mole. We have this nice benchmark of the melting and boiling points on the Celsius scale. And so now let's look at a reaction of water called autoionization. So auto means it kind of just happens. Ionization means that neutral H2O is forming two ions. And if I put these electrons in, on the product side, we formed a proton and then hydroxide. So that the elements are still there in those proportions, but now we have something plus and something minus. So we see in water that it starts with 2 lone pairs. How many lone pairs should be on hydroxide? For it to be negative, so 3. So if we had to account for how that happens, we know that a sigma bond is made up of 2 electrons. So this oxygen has 2 lone pairs. It needs a third one. So if we were to show how the electrons move, we would say from this sigma bond, the shared electrons in that OH go on to oxygen. So we use these type of arrows. It's called a curved arrow. I'll talk more in depth about this, but the arrow always starts at the source of electrons. So whether it's a lone pair, a sigma bond, or a pi bond, and it's pointing to something that can accept those electrons. We know from electronegativity that oxygen is more electronegative than hydrogen. So that oxygen is accepting those 2 electrons. And this might seem a little like minutia, but see how this arrow ends? So it's I'll say double-headed. That means the movement of 2 electrons. When we move into further modules in this semester, we'll see an arrow that looks like this. And so that only has sort of the one head to it. That's the movement of 1 electron. So make sure that you understand, what that is telling you. So the arrows, again, are used to show electron movement, and then from that, we're accounting for formal charges. And so from our Gen Chem learnings, that autoionization reaction, we can write an equilibrium expression. And so that's given the designation K, which I may have learned at some point in my life why it's K, but I no longer remember. But K is equal to the concentration of these product species divided by the starting material. So your proton, your hydroxide, and then your water. And another thing to point out, that's molarity, which is moles per liter. And that's typically how chemists write units, but if you take like physics, they'll do write it like that, which is liters to the -1 just means 1 over liter, and you get sort of the same thing. So since water is a pure liquid, its concentration has been found to be 55 molar. So that number is always that. And so you can just do some algebra and multiply both sides by this and fold this term into there, which eliminates this from the denominator. So that would be like, so that cancels out there, it gets folded into here, and then it's called KW. And so that leaves the product of the hydrogen or proton concentration times hydroxide concentration, and that's equal to 1 times 10 to the negative 14.
KW is a constant, right? Or that number?
This, yes. And so this number right here, this negative 14, should ring a bell for you, because that is ultimately translated to the pH scale. And as I said, with strong acids, the pH scale from 0 to 14 is fine. But when we're dealing with weak acids, they don't fall in that scale. And so then we have to do some figuring things out to make a scale that we can actually use for these functional groups. So for an aqueous system, if the concentration of proton is equal to the concentration of hydroxide, which of the following is true? Or what describes the system? So it's going to be neutral. So at that, using that 0 to 14, that would equate to a pH of 7. So if you have more acid, more proton than hydroxide, then the system is what? Acidic. And then obviously if you flip it the other way, it's basic. So these are the three situations here. And I think I'm missing a 4 here. That should be negative 14. So if we're just dealing with now these two species, proton and hydroxide, when you're comparing, the concentrations relative to one another, you can have acidic, neutral, or basic. So that leads us into these three theories of acidity now. And as you see in the fourth column in the table, the scope, I think Gen Chem primarily focuses on this first definition here, the Arrhenius, where you're either looking at proton or hydroxide as the acidic or basic species. That's pretty narrow because that's all you're measuring. A more general definition is the Bronsted-Lowry, and that says an acid donates a proton, and a base accepts it. So it's a little bit more broad. It encompasses most of the things in organic, but not all of them. And then finally, the Lewis, like the Lewis dot structures you've been drawing. That's the broadest definition of acid-base chemistry. And why is that? Because it's not focusing on any specific element or species. It's talking about the movement of electrons. A base in the Lewis sense is an electron pair donor. An acid is an electron pair acceptor. And so when we start pushing these arrows with the curved arrows, the Lewis definition is the best one to think about to understand mechanisms. So let's look at hydrogen chloride or hydrochloric acid in the presence of water. And let me put in some electrons. So, as I said, in these acid-base reactions, there's the acid. So water has to be the base. In the Lewis sense of the acid-base reaction, the base has to donate a pair of electrons. So one of these lone pairs on oxygen from water is going to abstract that hydrogen. So it's donating a lone pair of electrons. The hydrochloric acid, this bond is going to break between H and Cl, and that Cl is going to accept that pair of electrons. So that definition doesn't get into, any specific element. We're just talking about the movement of electrons. So in the curved arrow sense, we would start at a lone pair and say now we need to form an OH bond and we need to break an HCl bond. So electron source, electron sink, electron source, electron sink. Another way to rationalize this, chlorine is delta minus based on electronegativity. Hydrogen's delta plus. So electrons are attracted to something positive. And then this pair can go on to chlorine because it's already delta minus, and it can accept them and be happy as Cl minus. So if we put in our remaining lone pairs, we can see that ends up as chloride, that's the minus, and then hydronium ion. So, or we could write it H3O plus. So on the reactant side, we have acid base. On the product side, which one is the conjugate acid? So the hydronium ion is the conjugate acid, and then chloride is the conjugate base. To rationalize that, we can just apply that Lewis definition again. If chloride is the conjugate base, it has an electrons that can donate to abstract a hydrogen from hydronium. We then break an OH bond where those electrons go back onto this oxygen, so that oxygen accepts them. Any questions so far? So, as I said, the arrow has to start from the lone pair of the base. So it's donating that lone pair, and then this Cl is accepting it. Notice the flow of those arrows. So they kind of flow like start to finish, start to finish. If you're doing these sort of problems and you draw something that looks like that, that's no bueno. That's not good. Because that means, you're having a set of electrons and a set of electrons, so 4 total electrons kind of going into one spot. And, just due to the difference in electrostatics and Coulombic repulsion and all that, that's not going to happen. So we have the source and then the sink. So the double-headed arrow, that means the movement of 2 electrons. Whether it's a lone pair, that sigma bond or pi bond, that's 2 electrons. And I would definitely encourage you, in terms of the electron sink, you want to make sure that it's kind of jiving with electronegativity. Can the element or species accept those electrons?
So if they're always going kind of tip to tail, is there something we call that in-between thing that is moving? Or is it just electrons?
I guess to sort of, in a roundabout way, answer your question, like what would be in the middle there?
Right, because it's not a source or a sink.
Yeah, so let me answer it this way. So when we show these arrows, we're proposing a mechanism of how we think things are happening. So we're forming an OH bond, so we're making a bond. And then whatever that is pointing to, in theory, we need to break a bond. So in general, that's going to be, an atom or an element or something. So that kind of thing in the middle, you want to make sure that you're still obeying the Lewis dot rules for that element. Because you don't want to show an arrow where you're forming 5 bonds to carbon and then nothing else happens to break a bond. So we're still constrained by, the kind of normal bonding patterns that we draw the Lewis dot structures with. What I will say is, as this is drawn, this is a fairly straightforward mechanism, but as we learn more reactions, from starting material to product, these things, they happen very fast, but they don't happen instantaneously. So by very fast, I mean like 10 to the negative 12 seconds fast. In our span, that's very fast. But on a chemical reaction scale, it's kind of slow in the sense that between the starting materials and the products, there's kind of a black box where stuff happens. And then we'll start examining the energy required to get from here to there. So not only do we talk about the movement of electrons, we talk about the energy required to do that. Are there things that can exist between the starting material and the product? So just to highlight here, notice that HCl obeys all the definitions of an acid. It does increase the proton concentration in water. So we write hydronium like that, H3O+, but you can think of it as like a hydrated proton. Bronsted-Lowry, it's donating H+ to water, and then the Lewis, it's accepting the lone pair from water. So the definitions, as you move from narrow to broad, really all do align, and they don't contradict one another. So that was an example of water as the base with HCl. Let's generalize it to other things. So we talked about sulfuric acid to begin with, and we'll use this nomenclature here, just HA. So H is the acidic hydrogen, and then A is the rest of the molecule. So I'll draw the longest arrow in the world here, longest bond. So what I mean by that, so we're going to generalize this A to be whatever else is attached to that acidic proton. So really the same sort of arrow flow, water with an acid. It will always form hydronium. It can't do anything else. And then you get this anion, which is the conjugate base, so A minus. So in the first case, the HCl case, that was chloride. Here it would be hydrogen sulfate. Yeah.
Okay, so when you're saying that the oxygen, one of the lone pairs of the oxygen, it transfers to the hydrogen, and the hydrogen transfers to the acid, or how is it processed? Is it like the oxygen lone pair goes straight to the acid, or is it like a simultaneous process of interchange?
So again, it's probably not like instantaneous, because you don't start here and just end up there. There's a little bit of time that happens. So as these things approach one another, this lone pair is attracted to that. It just doesn't form a bond instantaneously. As it gets closer, the lone pair is kind of pulling this hydrogen away. So it's partially making this bond. And as that bond forms, this one gets longer, and then it gets weaker, and then eventually snaps. And then that sort of black box in between, we'll start talking about these things called transition states and intermediates. And those are reactive species that exist between the starting materials and the products. So one thing I do want to clarify about strength. a misconception coming from Gen Chem is that the concentration, so like molarity, is proportional to acid strength, and that is not the case. So like sulfuric acid it's sold commercially as like 98% sulfuric acid, 2% water. Hydrochloric acid's like 37% HCl and the rest is water. Those numbers, 98 and 37, don't correspond to strength. That's the concentration. An acid strength is the extent of ionization. So for our strong acids, when they're in water, how much of these are being formed? And that's not related to concentration. So if you're into it, you can take Chem 311, put that on your advising form next week with Dr. Miao. I know at least one person's going to take 461 with Dr. Guo. And so Dr. Miao will tell you about, this ionization. It's called activity coefficient, and Dr. Guo will overlay the mathematics of that to give you a better understanding. So for us, any strong acid dissolved in water is giving hydronium. So we can generalize this now to this equilibrium expression here. So this is our equation. Don't want to do that. This is our equation. We have hydronium, the conjugate base, and now the denominator is this HA. So remember, we're throwing that concentration of water into this Ka value as a constant. So this is what we're going to use to help us understand acid strength is this form of the equilibrium expression. So if we just do some thought experiments here, if the concentration of hydronium is greater than HA, what is the resultant acidity constant Ka? So really what you're doing is just making up some numbers and throwing it in there. So if we say hydronium is greater than HA, so let's just call that 1,000. We'll call that 1. So 1,000 divided by 1, that's going to get you a large number. We don't need any specific thing. We just want to see how that falls out of the equation. Stated another way, your acid in water is primarily producing this stuff over here. So there's a lot of this and less of that. So the extent of ionization is great, meaning that your Ka value is going to be pretty big. Now if we flip that and say the hydronium ion concentration is 1 and HA is 1,000, we put in 1 divided by 1,000, that's going to get us a small number. And so remember, what is the concept of a mole, Avogadro's number? We're talking about, a lot of molecules in there. So you're ending up with these really huge numbers or these really small numbers. And those can be kind of difficult to work with and understand practically. So we're going to do a modification of that equation to make our life a little bit easier. But here are those two scenarios. You have the hydronium greater than your starting acid. The fallout of the Ka is a very large number. That means the product side is favored at equilibrium. And so we call that a strong acid because it's ionized to a great extent. If there's not a lot of hydronium and most of it is just your acid, the Ka is small, so the reactant side is favored. And then we would say it's not ionized a lot, so it's a weak acid. So again, these numbers can get really ginormous or really infinitesimal, and so we want to normalize it. And the mathematicians came up with this first, and the other scientists started to use it to really scale things that are understandable in terms of the numbers, and that's the logarithmic function. So in chemistry, it's when you see that P, that means that a log has been applied to that. So pKa is the log of the acidity constant. And then you see that reflected on this side. So pKa is the negative log of the Ka, and so that's log base 10. So just a question, does anyone know who invented or discovered logs? It's either Euler or Napier, I think. One of those two dudes. So what ends up happening is there's kind of an inverse. It's due to the nature of that negative sign and the log. If you have a really large number, that Ka, and you put it in this equation, what it does is scale it down to numerically a small number. If you have a small number, you put it in there, you get a larger number. So you want to make sure that you understand the Ka, how the log affects that, and then ultimately how those numbers relate to strength. So we're going to be talking about the pKa scale for these functional groups. And from the strongest acid to the weakest, the numbers are bracketed from -10 to 50. So everything that strong acids, weak acids, all the functional groups lie within those 60 pKa units. The question? So remember when I said you're looking at a structure, you're talking about hybridization, attached hydrogens. Make sure that you write down what exactly that functional group is for that unique set, because then you're going to go to this pKa table. You're not going to find the exact type of hydrogen. You're just looking for the functional group, and then you're going to rank them according to acidity. The smaller that pKa value, the more acidic. So when you get up to like 50, those are the weak acids. So -10, I'll fudge it a little bit because there's a compound in here that's -14. So things that are negative are strong. When you get above 0 to 50, those are all the weak ones. So let's talk about the strong acids and then the line that we want to draw that will differentiate them from the weak ones. So again, strong acids. What the fuck? All right, got the red one. Strong acids are completely ionized in water. So again, all of them form hydronium, no matter what. So this table lists, the common ones that you've seen in Gen Chem. You might not have seen this first one, trifluoromethane sulfonic acid. That's the one with -14. And then the line is right here. So that's where the sign inverts. So anything less than 0 is classified as strong. 0 to 50 is weak. What you'll notice with all of these, a term that's used, if you look at these formulas, these are classified as like mineral acids. Notice none of them have any sort of CH bond. So perchloric, hydroiodic, sulfuric, hydrobromic, hydrochloric, hydronium, nitric. There's no CH functional groups below 0. So that means they're all down here off the slide onto the whiteboard there. So if you want to practice, what you can do is, draw these out, the Lewis dot structure, show them reacting with water to form the conjugate base plus hydronium. So if you want to kind of have a benchmark, hydronium is a good value to remember. -1.74, or if you're ballparking it, just -2 is good enough. So I think we're going to look at the trifluoromethane sulfonic acid, because that's our kind of bracket at -14, the most acidic. Maybe let me just draw that out here real quick. So there's trifluoromethyl sulfonic acid, and that's what you've seen before, sulfuric acid. So they both have OH, but sulfuric acid here is at -9. Why is that one more acidic? And let me go crazy with the colors here. They both have that. But then that thing in yellow and that thing in red are different. So knowing what we know about electronegativity and bonding, how can we explain why does that CF3 group make that more acidic than when it's just OH? So the electronegativity is playing a big role in it. And as a fallout of that are these two other terms, resonance and induction. So here's the arrow pushing for that when we have the acid plus water. So the water is being the base to abstract that hydrogen. We're breaking this OH bond, and those electrons are going on oxygen. So one thing I want to highlight here, at equilibrium, this is going to shift 100% towards the products. So again, equilibrium is the state at which things aren't changing anymore. So again, try not to get confused thinking that it's 50-50. It can be some other ratio, but at some time there's a state that's reached, and for this one, the reaction's irreversible, meaning it's not going to go the other way. So one thing we're going to do is look at this conjugate base. What is special about that structure that makes this more acidic than sulfuric acid? So the first factor is going to be resonance. So when that oxygen accepts the lone pair, it gets a negative charge. Because it's an ion, it's going to be a different energy than what it started with when it was neutral, right? So that negative charge, if you want to think about it, it's kind of not happy. But because sulfur has a higher valency with these other SO double bonds, we can delocalize that lone pair onto either of those other oxygens. So rather than just one oxygen being unhappy, misery loves company, and it gets spread around to the other two. So that stabilizes the conjugate base. And then through inference, it's making the acid stronger. So anytime you can stabilize, a negative charge or a positive charge through these resonance hybrids, it makes things more content or stable. And so again, this arrow pushing, we're starting at a lone pair. We're now going to make an OS double bond, and then we're going to break an SO pi bond where the electrons go on oxygen. So that negative charge migrates. Sulfuric acid, its conjugate base can have resonance as well, but the thing that sets this one apart is this concept of induction. And really with that CF3 group, the carbon bearing the 3 fluorines, we know that fluorine is the most electronegative element on the Pauling scale. So we can assign those delta minus charges to it. And really what that is, what I'll draw on those blue bonds, those fluorines can sense that negative charge. And the sigma bond network is kind of like tug of war. It's helping to stabilize that negative charge, because fluorine's electronegative, it's greedy, it wants as much as it can get. So the induction is a through bond effect. And really it's based on electronegativity. In the series of 4 compounds here, you'll notice they all have this SO3H group, and then they differ by the number of fluorines attached to the carbon. So this was the 3. Its pKa value was -14. If they're all hydrogens, it's -2. So really what we're doing is taking an H, substituting an F, then 2, then 3. So the more of those you put on there, the more the acidity increases. And so why are there no values here? Because I'm lazy and I have not looked them up. But you can rest assured they lie between that -14 and -1.2. So just like, remember with the chemical shifts in NMR, when we're talking about how the heteroatom affects how it moves that away from 0. So if you have, this electronegative element and you keep moving it further and further away from the acidic site, the magnitude of that induction decreases. So if you start putting a bunch of carbons in between, the acidic site and the electronegative site, it doesn't have that great of effect. I must have taken the slide out. I thought I had an example. Let me just illustrate that. So here you have 1 carbon, then the fluorine, so now you have 2. And so as you increase that length, that tether between the acidic site and the heteroatom, the effect of its induction weakens. It's not as strong. Any questions so far on resonance and induction? So again, these are all the factors that are affecting the strength. Let's look at another one. It's slightly different, related to some periodic trends. And these deal with these mineral acids HX, where X, again, is a halogen. Anyone know which one of these Jesse and Heisenberg used in Breaking Bad? So they were doing some stuff and they used HF. So I think there's a general misconception that hydrofluoric acid of this series is the strongest. But when you look at the pKa values, the HI is the strongest. Again, using this pKa. So hydroiodic acid has a pK of -10. That's the strongest in this series. You might think that, well, since fluorine is the most electronegative, that should be the strongest acid. There's a couple things going on with this series. The size of the hydrogen stays the same, so that's constant. But from F to Cl to Br to I, what happens to the size of the halogen? The radius is getting bigger. So if you kind of think of the hydrogen as the size of like a golf ball, so that stays the same. Then fluorine is maybe, a softball. Chlorine is, I don't want to get too crazy here. I don't know, maybe a dodgeball, a little bigger, a little squishier. It's bigger than a dodgeball. I don't know. I want to use a beach ball for iodine because it's really big, but that proton is still a golf ball. And remember, you're still forming a bond between them. So look at the bond length that's increasing. So another way to think about acidity, that hydrogen is being donated. With HI, that bond length is really long to begin with. So there's really not a lot of orbital overlap because hydrogen's in, period 1 and then iodine's way below. They don't have the best orbital overlap to begin with. And so it's you can think of HI as like H plus and I minus to begin with. And then HF is more of a polar covalent bond. So it's that bond length, then how much the electrons are shared. And then the other thing about the X minus that's formed, so because that atomic radii increases, I like to think of, I minus is big and squishy. And so there's this other term called polarizability. And that's just the ability of that anion to accept those electrons and be happy about it. So fluorine will accept them, but between that polarizability or squishability, there's another way of talking about acid-base theories called hard and soft in terms of, what's really going to take those electrons and be happy with it. We won't go too much into that definition, but those are some of the factors that affect acidity. And we only got about a minute left. But where we're going with this is, what about all the functional groups, the weak acids? Do I have acids? And so that's what we'll talk about on Monday. Where do all these functional groups lie between 0 and 50? And why are they resolved amongst those pKa values? In there, take the slide out.